So welcome once again to YouTube land, and today we're going to be going over your day 6 notes in your unit 2 packet, specific heat calculations. That'll be on page 14, and then the homework assignment follows on page 15. Just a couple of other reminders. We'll do a little bit of extra practice with these specific heat calculations tomorrow. And your packet had a couple of errors on the dates for next week. Next Monday is the 17th and the 18th. So the test is coming up on next Tuesday, and that means that the study guide is due on Monday. So just make sure that you get that done so you get your 5 bonus points secured for the test grade. All right, so go ahead and flip over to page 14. And we'll go ahead and do the warm-up. So think about going to the swimming pool on a warm summer day, and I'll go ahead and pull up a picture to help engage your memory here. All right, so think about going out to the swimming pool on a summer day and compare the temperature in the mid-afternoon of the stone or the cement that is around the perimeter of the pool to the temperature of the water that's actually in the pool itself. All right, and so pause the video for a second and go ahead and answer the question, which is which of these substances feels hotter in the afternoon and why you think that is the case. So go ahead and pause and answer. Okay, so I suspect everybody probably said, of course, the water feels cooler, and obviously the water is indeed at a much lower temperature than the concrete around the pool, which might be hot enough to burn the bottom of your feet if you're standing around for too long on it. The more important thing is why. Why is the water cooler? Because if you think about it, assuming it's not a shaded pool, it's all getting exposed to the exact same amount of energy, ultimately sunlight. Right? It's not like the sun is all of a sudden hotter when it shines out here on the concrete and cooler on the swimming pool. It's all getting exposed to the same amount of solar radiation. And so why does the water stay at such a cooler temperature versus the concrete? Clearly there must be something different about the way that concrete reacts to solar radiation than water, right? And so that the difference can be attributed to this property that we're going to talk about called specific heat. All right. Each substance has essentially its own unique way of how it reacts to heat. Substances are very slow to adjust their temperature. That is like water, right? Water heats up very, very slowly when it's exposed to heat. But some other substances like concrete heat up pretty quickly. They don't take that much energy for their temperature to shoot up to quite a high number, right? If you think about like the handle, the metal handle on the swimming pool rail, or if these little recliners have metal in them, then they're going to heat up even quicker. They have an even lower specific heat, but of course something like water has a much higher specific heat, and so it's much more sluggish to change its temperature. All right, so obviously, we said the water is going to require a lot more energy to raise its temperature during the afternoon. All right, so here's the formal definition of specific heat, which is the amount of heat needed to increase the temperature of exactly 1 gram of a substance by exactly 1 degree Celsius. All right, and here's a list of some common specific heats. You don't need to write these down in your notes, but most of these are metals. You can see aluminum, copper, gold, iron, lead. All have fairly low specific heats, less than 1, right? When you look at ice, it's 2.06, right? Steam is the same, right? And then liquid water has a specific heat of 4.18. So of all the things on this list, liquid water actually has the highest specific heat, which means it requires more energy to change temperature, and if it's exposed to, a constant level of heat, then it's going to take a lot longer for its temperature to change compared to the substances that are around it. Okay, so the formula for specific heat is right here. Actually, this is the formula for heat in general. Specific heat is symbolized by the lowercase letter c, and the little p next to it is not particularly important for you guys, but c is the letter for specific heat. And the overall equation for the amount of energy that is involved when something either heats up or cools down is Q equals mc delta T. This is the Greek letter delta, this triangle symbol, and we'll see that a lot in chemistry. It simply means that whatever variable follows the triangle, the letter delta, is changing. So we're not just multiplying these numbers by one temperature, we're multiplying by a temperature change. So to figure this out, we're going to need an initial temperature and a final temperature, which we can subtract and obtain a difference in temperature, which is what that triangle is instructing us to do. So again, here's your equation for heat calculations, and then here are all the definitions for the different variables, right? So Q is in joules, C is the specific heat, which is kind of a complicated unit. It's joules per gram degree Celsius, or it could be calories per gram degree Celsius. Remember that we can use joules or calories when we're talking about energy. M is the mass in grams, and then delta T, that is the change in temperature. So for example, if I heat something up from like 30 degrees to 50 degrees Celsius, then that delta T would be 20, right? I just subtract my final temperature from my initial temperature, and that'll give me my delta T. All right, winter's not coming yet, but Lord Stark does tell you that word problems are. Okay, so look at the bottom of page 14, and we'll work through some of those examples together. So remember, when we solve these, we're going to be using the guess method. We went over this the other day, but the first step, G, we're going to identify the given information. My students, I'm just saying y'all can circle it and assign a variable, right? U, that's for identifying the unknown. I told y'all you can underline it. Once again, assign a variable to the unknown. E is write out the equation. S, you're going to substitute your numbers and solve, and then the last S is really for solve, and specifically make sure you give a unit and make sure that you round your answer to the correct number of significant figures, which is why we spent all that time a couple weeks ago going over the rules for this, so don't forget those. All right, so let's go ahead and take a look at practice problem number 1. Okay, how much energy is required to raise a 34.0 gram sample of copper metal from 20 degrees Celsius to 45 degrees Celsius? Specific heat of copper is given as 0.385 joules per gram degree Celsius. So first thing, we just look for the givens. Okay, so just circle the numbers and the units. Okay, 34.0 grams, I should know because it says grams that that's a mass. So I'll assign it the letter M. Okay, I know 20 degrees Celsius, that's a temperature, and it says raising copper metal from 20 degrees Celsius, so I know that's my initial temperature. I'm just going to call that T1. I'm raising it to 45 degrees Celsius, so I know that is T2. And then the specific heat for copper is 0.385 joules per gram. So that is my specific heat. Remember, the letter we give that is little c with a little p next to it, specific heat. All right, so those are my givens. How about my unknown? That's energy. Being asked to find energy, and in our formula, energy, heat, is represented by the capital letter Q. So I'm going to write Q above heat. Okay, so now I just need to write my formula. My formula is Q equals mc delta T. All right, well, to get delta T, I need to go ahead and subtract T2 minus T1. always subtract your final temperature minus your initial temperature. All right, so it's always going to be T2 minus T1. So I'll just do that kind of over here on the side. 45.0 minus 20.0. Okay, and that's going to give me a difference of 25.0 degrees Celsius. So that's going to go in there for delta T. All right, so I've done step 3. I've got my equation. My fourth step is going to be to go ahead and substitute. So I'll do that kind of over here. Q equals my M is 34.0. Okay, I'll put everything in parentheses. My specific heat is 0.385 joules per gram Celsius. And then my temperature difference is going to be 25.0. Okay, so there's my 3 numbers that I need to multiply. And when I do that, my equation says that's going to give me the heat. Okay, so I'll go ahead and plug those numbers in on my calculator here. Okay, so I got 34 times 0.385 times 25.0. Okay, and voila. Okay, I got 327.25 as an answer. Okay, now just to kind of save a little space, let's talk about, remember your last step, make sure we round to the correct number of significant figures. All right, so look back at your givens, and it's really best to look back at the original information given in the question in case maybe you wrote down 34 here instead of 34.0. Look back at what the question actually gave you. Okay, that's 3 sig figs, right? That 0 counts because there was a decimal, right? That's 3 sig figs. That's 3, and that's 3, right? So guess how many my answer is going to have? 3. So I take a look at what my calculator gave me. 327.25. The third sig fig is the 7, so I'm rounding this to the ones place, in other words, to the closest whole number. So my correct answer should be 327. Well, 327 what? Right? Got to have a unit in the answer in addition to the right sig fig. So what would my unit be? Well, the key is, when you're solving these things, go back and look at your specific heat. Because remember, specific heat can either be given in joules per gram degree Celsius, or sometimes it can be given in calories per gram degree Celsius. So the unit for your specific heat will tell you what the unit for your heat should be at the end of your answer, right? So since my specific heat was given in joules per gram, guess what? My unit's going to be joules. If it had been calories per gram degree Celsius, then this would be calories. And there's a big, big difference between 327 joules and 327 calories. So if you don't have that unit right, then your answer is pretty useless. Okay, now we calculated a positive answer here. Okay, so what that means is heat is being what? Is heat being added to my copper, or is heat being removed from my copper? Well, since delta Q, or Q rather, was positive, heat is being added, right? So from the perspective of the copper, this is an endothermic process. When Q is positive, then heat's going into your system, okay? So let's take a look at example number 2. How much heat's released when a 3.20 gram sample of water is cooled from 83.0 degrees Celsius to 54.0 degrees Celsius? Specific heat of water is 4.18 joules per gram degree Celsius. Okay, let's look at our givens. That's my mass. That's my initial temperature, T1. 54.0. That's going to be my final temperature. Call it T2. And my specific heat for water is 4.18 joules per gram. So we're going to call that CP. All right, so let's take a look at what's next, the unknown. Okay, well, the unknown, again, is heat. So kind of underline it, kind of hard to do that there, but underline heat, and that is the letter capital Q. Okay, so let's write down the equation. Go ahead and put in Q equals MC delta T. Forgot my P there. All right, so there's my equation. Before I can do anything, I need to know what delta T is. Remember, that's our change in temperature. So once again, to find delta T, I'm just going to subtract my final temperature minus my initial temperature. So always T2 minus T1. So don't just be tempted to always assume, okay, I'm going to put the bigger number first. Okay, it's always final minus initial. So it's 54. Oops, sorry, should be down here. 54.0 minus 83.0. So what does that give me? That gives me a negative number, right? 54 minus 83, that's negative 29 degrees. What does that mean? My delta T, my temperature, has dropped by 29 degrees. And you might guess that's going to give me an overall negative answer, because mass is always positive, specific heat's always positive, but if you've got a negative right here, it's going to give you a negative answer overall. Right? So we can already kind of predict what's going to happen right here. Heat is being lost by my sample of water since it's cooling. Let's go ahead and plug in the numbers and figure out exactly how much heat is lost. All right, so M is going to be 3.20. Specific heat is 4.18. And my delta T number is negative 29. Now I did make a mistake there. I should have the same number of decimal places, so I should have negative 29.0 degrees as my drop in temperature. So I make sure I put that negative there, negative 29.0. And then I can go ahead and multiply those three things out and get my answer. All right, so go ahead and do my work on the calculator. Okay, 3.20 times 4.18 times negative 29.0. Okay, and I got my answer, negative 387.904. All right, well, let's go ahead and round it to the correct number of significant figures. So how many should that be? Well, I've got, look at my original givens, 3 sig figs here, 3 for my temperatures, and 3 for my specific heat. So once again, it's 3. All right, so I'm going to round this one to my closest whole number. 7 is going to round up. So therefore, my answer, Q, is equal to negative 388 what? Well, once again, I have joules for my specific heat. It's joules per gram degree Celsius. So therefore, I want to have joules as my answer. You might wonder, well, why don't I use all these other things, grams and degrees Celsius? Okay, those things end up canceling out. I'm not having you plug in all your units here, even though you probably should, but you can trust in the end that everything cancels out except for joules. All right, so that's going to be your answer that you want to box. Okay, and we said since heat delta Q, Q is negative, so that means that our overall system, our water, is losing heat. So heat is being lost from the system. Okay. For number 1, heat was being added to the system. So this one, since you got a positive answer, was endothermic. And this one was exothermic, because heat went out to the surroundings. All right. So now just go ahead and flip over to page 15. All right, and you got 6 homework problems to do. So for each of these, make sure you go through the guess method. Okay, find your givens, circle them and give them a variable. Find your unknowns, underline it, give it a variable, and then go ahead and write the equation. substitute, solve. Okay, make sure that you subtract T2 minus T1 to get your delta T, your temperature difference for your equation. And I believe all of these homework problems, oh, nope, there's one, number 5. This one's tricky. Okay, what's tricky about this? Well, you're not solving for, oh, never mind. No, this isn't tricky. I'm just getting tired. All right, they're basically all the same as the examples that I gave you on the first page. So go ahead and work through your homework. Try to get these knocked out before class is over. And good luck studying for your test next week. All right, so thanks for watching. What I'm asking people to do on these videos now, if you like it, that's great. Give me a like. But what I'm really asking people to do, so I can kind of gauge how many people are using this, is go ahead and leave a comment. All right, and in your comment, all I care about is just put your name and your class period. That you don't have to say anything, but just give me your name and class period, and that lets me know kind of who's actually using these videos and what classes are benefiting from them. And if I have a lot of people signing in and leaving their names and periods, then I'll continue to make them. But if not, then probably I won't. All right, so thanks for watching, and I will see you next time.